example results. The plan was a break at 11.
Okay.
So I'll go through the example results, and then I have the 2 more sections to kill after that. So we're a little bit behind schedule-wise, but not too bad, because we're getting good questions and good discussion. But if I go through the results, this one I think are good to see when you're tired, because I want to make sure we go through the uncertainties, you're awake. And it really is, it's just showing how things look at different sites. So White Sands, the reason we went away from White Sands is all of these wonderful little geologic features that geologists like to play with. I don't want to see when I'm doing reflectance measurements. Railroad Valley down here in the lower right, Ivanpah Playa in the upper right. Roach Lake is very much like Ivanpah Playa, it's just a few meters north. The very first time we tried to do an astro calibration, we were not allowed to go to Ivanpah Playa, it was too wet, so we quickly drove out to another site. You can start to see some of the noise in the water band. That depends on how dry or how moist the day is. But again, you can start to see some of the uniformity differences. Ivanpah in this case is much more uniform than, say, White Sands. But White Sands, what's nice is that non-uniformity does not really increase your uncertainties. It just makes it noisier, but all you're doing is you're averaging so many data points that it really doesn't impact your characterization of the sensor. Putting them on one graph, and this includes now Railroad Valley, Ivanpah Playa, the BV is Barrios Blanco, which is a playa down in Argentina that was used for Hyperion, on the White Sands. What you start to see is White Sands can be very, very bright, and it also is whiter than the other materials, but the fall off was something we did not want to work with. The rest of these is a bunch of differences between spectrometers. And so it gives you an idea of if I collect data at a given site with different instruments, I collect data at the same site with the same instrument multiple times. If I collect data of different days with the same instrument at the same site, and looking at how things change as a function of time. So this green line here is looking at 2 different instruments walking the same site. And this was the one that when we went back and looked at it, we realized was the reason that, or pointed to the reason we were having that odd behavior for Landsat at day 1500. It's a nonlinearity effect in the detectors. And because it should have been optimized, but the optimization scheme does not force us to do it, and so we started collecting data, and one of the spectrometers was going fine, and the other one wasn't. The 5% difference, that is not that bothersome either, because it's a very large area that we're covering. This site, this is the 1 kilometer site. So you would expect to have some differences, but still 5% difference is larger than what we would have liked to have seen. But if you have a 2% and a 2%, it's not outside the bounds of reality. It should not scare you that much. But what was very odd is if we go ahead and we do 2 collects on the same day with the same instrument on the same site, but at different times, they repeated reasonably well. So there's some odd things that happen, and you can say, well, is it the panel, is it the difference in the EXT, but there should not be any difference at all. You should get the same answer with different radiometers because you're doing a ratio technique. And this is always what's been bothersome. This little blip here tells us that one of the instruments was not warmed up properly, so there's a temperature effect in the blue part of the spectrum, but it didn't show up at 1,000 nanometers, whereas the other one, you can see where there's a joining of the 2 spectrum, the silicon out into the indium gallium arsenide. On one of the collects, it hadn't been warmed up as much as the other collect. So looking at, again now, Ivanpah Playa, this is a small area. This is a 300 meter by 80 meter area. And looking at, again, 2 different instruments, 687 to 6014. The 687 is the one, that's the older version. So that's the one that was most likely the problematic one. If we would go back through and remove all of those data from the Landsat archive, we'd probably get rid of that bump. So you see this feature here. The blue thing there is because of the warming effect. You have issues with absorption in the atmosphere causing signal noise problems. Real site effects. So basically there are 3 different dates. August 18, August 19, and August 23rd. 18th and 19th. The system was collected basically the same site, same way, same instrument. Agrees within a few percent, except out here in the shortwave infrared. And part of that is, you basically blame it on temperature effects or odd behaviors with the instrument. But then it rained and the reflectance changed. So this is why we characterize the surface, because we want to know about that 5 to 10% shift. So this is a real change that happened for different days. The question is now you start talking about what happens. Again, you have now the collection that was done. And, this was August 23rd for Lotus. And the problem was that one of the other dates we needed this collect to use it, but because of the rain, we couldn't go back in time. And this is the problem: is you're trying to do 6 or 7 sensors on one trip, and you have one spectrometer, so you make choices of, well, I'm going to go ahead and I'll collect here today, and I'll collect there tomorrow, and I use tomorrow for today. And it came back and it cost us because we had a change in the site between the 2 days. One of the really annoying things that we noticed at Agapop Playa, though, was we would collect multiple times over the site. And it started when we started doing Landsat, and we started doing Hyperion. So we were doing Hyperion, which was at the Landsat overpass time, and we were doing Aster, which is at the Terra overpass time. They were 30 minutes apart. So we would collect the site once, and then we would collect it again. And the reflectance always went up. Always went up. And so we said, well, that doesn't, so let's go ahead and we'll take a small area and we'll go ahead and collect. So each of these runs, the results are ratioed to the first run, and it's percent difference relative to that first collection. So run 2, 3, 4, 5, 2, 3, 4, 5. The reflectance is increasing with time. We collected this, and then every time we would try and find out, is it indeed purely because of the BRF effects, we wanted to put the radiometer and look at the ground. Either clouds, instrument failure, or some other impact happened that we could never tie it down. The answer is yes, this was a BRF effect or instrumental effect. And this is the problem with real life when you start doing field work, is when you find these 0.5% kind of things that are bothering you, it takes a very strong effort in order to actually solve the problem, because you have no control over the situation. So that's one of the interesting things of that. Day-to-day repeatability. So this is the same instrument measuring the same site. In some cases it's parts of sites, it's sometimes because it's the 1 kilometer area. And in some cases it's day-to-day, and in other cases it's the same instrument the same day, but basically this is plus minus 2%. And so there's one system here where it started to overheat. You get problems with the behavior of the radiometer. But this really is, this is, if you're careful and you know what you're doing and you're doing what you should be doing, it's very repeatable, especially the mid-visible, because that's where I'm going to do all my uncertainty analysis, because detectors get strange out of the short wavelengths, they get strange out of the long wavelengths, we get noise problems we have to deal with. But later on, you're going to see, well, we think we can do plus or minus a few percent in terms of repeatability. And this is where a lot of that comes from. Yeah.
So these are all relative differences, 2, 3%, whatever it might be. What are the absolute values? How significant actually are these few percent?
So this is at 0.35 to 0.45 reflectance. So it's small reflectance values.
Right.
It's